Hello everyone, I am Supin Lu. I come from Taipei, Taiwan. I am pleased to introduce my paper. The title is A Decentralized Gas-Free e-ticket tourism system with Dynamic Security, a blockchain-based approach. The paper outline are as follows. Introduction, background, and the main is the system overview. I will introduce the key component in the paper. The follows is dynamic group key mechanism. In the then I will talk about system workflow, security analysis, comparison with existing systems, scalability considerations, and the final is conclusion and future work. Tourism industry undergoing digital revolution driven by blockchain. There are some current e-ticket system limitations. For example, high transaction costs, security vulnerabilities, and centralized management. High transaction costs, variable fees affecting affordability. Security vulnerabilities is susceptible to fraud and hacking. Centralized management has single point of failure, limited flexibility. Therefore, we can think about the blockchain potential solutions. This is because decentralized nature enhances security and transparency. Immutable record keeping improves trust and auditability. However, there are some challenges for the solutions. For example, transaction costs, scalability. Transaction costs for public blockchains limit widespread adoption. Scalability issues for high capacity ticketing operations. Now we talk about the background. We will talk about the blockchain technology, Ethereum and the smart contract, and the proof of authority, or we can say it POA consensus. Distributed ledger technology enabling secure and transparent transactions. Blockchain eliminates need for central authority, enhancing trust and efficiency. And blockchain platforms supporting self-executing contracts. Smart contracts automate agreement terms. It can reduce intermediary risks. Then we talk about the proof of authority consensus. The POA consensus mechanism using pre-approved validators. The consensus is faster and more energy efficient than proof of work. The proof of work is used in Bitcoin. POA consensus also enables gas-free transactions. It can improve cost-effectiveness. Now we have some overview about our system, design goals and key features. We have three design goals: eliminate transaction fees, improve security, and decentralize e-ticket. We want to utilize POA Ethereum network for gas-free transactions. We also want to reduce costs for both tour operators and tourists. In addition, we want to implement a dynamic group key mechanism. This means that when the group member joins or the group member leaves, the group key will be updated. We also want to enhance protection against fraud and unauthorized access. In addition, we also want to remove a single point of failure and increase system resilience and flexibility. In the paper, we also have four key features: get-free transactions by POA network, dynamic group keying for enhancing security, decentralized architecture, improving system robustness. In addition, user-friendly solution for tour operators and tour. There are four key components in this paper: that decentralized application, Node and .js server, smart contract on Ethereum network, and the POA parity authentication network. That runs in user browser, providing intuitive front-end interface. In addition, that enables direct interaction with blockchain network. Node.js acts as off-chain intermediary. Besides, it simplifies interaction between user and the blockchain. In addition, it also enhances performance and reduces on-chain operations. Smart contract on an Ethereum network manages membership registration, ticket purchases, and key update. Also, written in Solidity can ensure transparent and immutable operations. And the POA parity authentication network operates as private Ethereum network, and the POA parity authentication network enables gas-free transactions through trusted validators, and it also balances security, efficiency, and decentralization. Then we talk about the dynamic group key mechanism. Here is a concept of the algorithm overview. It uses kcap 256 hash function for key generation and incorporate current time step and random values for unpredictability. The key update scenario have some cases: new member joining, member leaving, or a regular key update. The new member join can ensure new member can't access past communications. And when member leaving the group key prevents departed member from predicting future keys. And when we talk about a regular key update, this can maintain the forward security and limit potential key leakage impact. Here is the system workflow. There are 7 steps for the system workflows. The first is user interaction initiation, then DApp and server communication. The third is group key generation, and the fourth is smart contract invocation, and then blockchain processing. The next is result propagation. And finally is group key distribution. Then we talk about the security analysis. The key properties are key secrecy, forward secrecy, backward secrecy. And we also have some theories and the proof sketches in the paper. The key properties such as key secrecy, forward secrecy, backward secrecy. There's key secrecy ensures group key known only to legitimate members. Forward secrecy past communications remain secure if current key compromised. And then, backward secrecy, it means that future communications are protected if the current key is paused. We also have some theories and proof sketches in the paper. Leverage one-way properties of K-cap 256 hash function. Also incorporate unique random element in key generation. Also ensure computational infeasibility of deriving past or future keys. Then we compare reason with existing system. There are some key advantages of a proposed system. For example, combines speed and scalability of centralized systems. Incorporate secure and decentralization benefits of blockchain. Eliminate transaction costs through POA consensus. Now we have some consideration about scalability. For example, network congestions, key distribution complexity, validator availability, and POA trade-off. A network congestions, the challenge is transaction volumes surges during peak travel seasons. The solution might be implement layer 2 solutions, for example, state channels for off-chain transactions. The second key distribution complexity considerations. The change is increasing complexity with growing user base. The future work is develop efficient multi-point distribution protocols. And then the data availability. The challenge is ensuring continuous availability of trusted validators. The solution might be maintain geographically distributed validator network. And then we talk about POA trade-off. The challenge is balancing scalability, security, and decentralization. The risk mitigation is implement validator rotation and strict selection criteria. Here is the conclusion and the future work. The achievements of the paper are developed gas-free e-ticket system using POA Ethereum network, enhanced security through dynamic group key mechanism, implemented decentralized management structure, improves efficiency and scalability compared to existing solutions. The future research directions are explore integrations with other blockchain-based travel services, investigate advanced layer 2 scaling solutions, develop sophisticated multi-point key distribution protocols, optimize validator selection and rotation strategies, or conduct real-world pilot studies to validate system performance. There are some potential impact. Revolutionize tourism industry by enhancing in-ticket security, efficiency, and user experience. Our pathway for broader blockchain adoption in travel and hospitality sector. Here are the references, and thank you for listening.